4,300 light-years away, a planet orbits so close to its star that its skies whip winds faster than the speed of sound. But that's not the strangest part. In this alien atmosphere, molten glass condenses in the sky and rains sideways at thousands of kilometers per hour. Imagine standing on a world where the very air around you is filled with microscopic shards of glass, moving at velocities that would instantly shred any material we know. The temperature is hot enough to melt copper, and the winds blow with such fury that they dwarf the most violent hurricanes on Earth. This isn't science fiction. This is HD 189733b, one of the most extreme worlds we've ever discovered. Today, we'll explore the physics and science behind one of the most terrifying yet fascinating weather systems in the known universe. We'll dive into how we discovered this nightmare planet, what creates its sideways glass storms, and what studying such hostile worlds teaches us about the incredible diversity of planets beyond our solar system. This is a world where the laws of physics create conditions so extreme that they challenge our understanding of what's possible in planetary atmospheres. A place where beauty and violence dance together in the cosmic darkness, creating storms of liquid glass that paint the sky in brilliant blue, while simultaneously making the planet one of the most inhospitable places in the galaxy. Get ready to journey to a world where it literally rains glass, and discover how scientists unraveled the secrets of this alien storm system from thousands of light years away. Our story begins in 2005, when astronomers using the radial velocity method made a discovery that would fundamentally change our understanding of extreme planetary weather. Located approximately 64 light-years from Earth in the constellation Vulpecula, they found something extraordinary orbiting a star designated HD 189733. This wasn't just any ordinary planet. What they discovered was a world so alien, so fundamentally different from anything in our solar system, that it challenged every assumption we had about planetary atmospheres. The planet, designated HD 189733b, belongs to a class of exoplanets we call hot Jupiters. But even among these extreme worlds, this one stands out as particularly remarkable. The discovery team, led by astronomers from the Geneva Observatory, had been systematically searching for exoplanets using the high-accuracy radial velocity planet searcher, known as HARPS, installed on the European Southern Observatory's 3.6-meter telescope at La Silla Observatory in Chile. They had no idea they were about to uncover one of the most weather-beaten worlds in the known universe. When the first radial velocity measurements came in, the astronomers knew they had found something special. The signal was strong and clear, indicating a massive planet in an incredibly tight orbit around its parent star. But it wasn't until they combined these measurements with transit photometry observations that the true nature of this world began to reveal itself. To understand just how extraordinary this planet is, we need to first grasp what a hot Jupiter actually means. Imagine taking our own Jupiter, a gas giant so massive that it contains more than twice the mass of all other planets in our solar system combined, and then somehow moving it incredibly close to the Sun. So close that it completes an entire orbit in just 2.2 Earth days. That's what we're dealing with here. The very existence of hot Jupiters was once considered impossible by planetary scientists. According to our understanding of planetary formation in the 1980s and early 1990s, gas giants could only form in the cold outer regions of stellar systems, where water and other volatile compounds could freeze into solid cores massive enough to gravitationally capture the thick atmospheres we see on Jupiter and Saturn. The idea that a gas giant could exist just a few million kilometers from its parent star seemed to violate everything we knew about how planets were born. Yet here was HD 189733b, defying our preconceptions and forcing us to completely revolutionize our theories of planetary formation and migration. Scientists now understand that planets can migrate inward from their birth locations through gravitational interactions with the disk of gas and dust from which they formed, or through gravitational encounters with other planets in the system. The discovery process itself was a marvel of modern astronomy that showcases the incredible precision required to detect worlds orbiting distant stars. Scientists use the radial velocity method, which detects the tiny wobble that a planet's gravity creates in its parent star. As HD 189733b orbits its star, its gravitational pull causes the star to move back and forth by just a few meters per second. To put this in perspective, that's slower than a person walking. This creates a Doppler shift in the star's light that sensitive spectrographs can detect. It's like listening for the almost inaudible whisper of a giant planet tugging on its star from across the cosmos. The precision required for these measurements is absolutely staggering. Astronomers had to account for the Earth's rotation, its orbit around the Sun, the motion of the Sun through the galaxy, and countless other factors that could introduce false signals into their data. They had to measure changes in stellar motion that are smaller than the speed at which a tree grows, all while looking at a star that's over 600 trillion kilometers away. But the radial velocity detection was just the beginning. What made this discovery truly special was that astronomers were able to confirm the planet's existence using transit photometry. This means that from our perspective on Earth, the planet actually passes in front of its star, causing a tiny but measurable dimming of the star's light. The probability of a planet's orbit being aligned just right for us to see these transits is incredibly small, making HD 189733b's favorable geometry a stroke of cosmic luck. This transit method allowed scientists to determine not just that the planet exists, but also its size, density, and orbital characteristics with remarkable precision. When a planet transits its star, the amount of light blocked tells us exactly how large the planet is relative to its star. The duration of the transit reveals details about the planet's orbital speed and distance from the star. Multiple transits allow astronomers to determine the orbital period with extraordinary accuracy. The numbers themselves tell an incredible story. HD 189733b has a mass of approximately 1.14 times that of Jupiter, making it slightly more massive than our solar system's largest planet. Its radius is also about 1.14 times that of Jupiter, which tells us something fascinating about its density and internal structure. Despite being more massive, the planet is only slightly larger, indicating that the extreme heat and proximity to its star haven't caused it to expand as dramatically as some other hot Jupiters we've observed. This relationship between mass and radius provides crucial insights into the planet's composition and internal structure. The fact that it's denser than some other hot Jupiters suggests that it may have a more substantial rocky or metallic core, or that its atmosphere is more compressed due to the intense gravitational and thermal environment it experiences. The parent star, HD 189733, is what astronomers classify as a K-type orange dwarf star. It's smaller and cooler than our Sun, with a surface temperature of approximately 4,800 degrees Kelvin compared to our Sun's 5,780 degrees Kelvin. The star has a mass of about 87% that of our Sun and a radius of about 76% of our Sun's radius. While it might seem like a smaller, cooler star would create less extreme conditions, the proximity of the planet more than makes up for any reduction in stellar energy output. This proximity is truly mind-boggling and represents one of the most extreme orbital configurations we've discovered. The planet orbits its star at a distance of only about 4.6 million kilometers. To put that in perspective, that's about 12 times closer than Mercury orbits our Sun, and about 40 times closer than Earth's distance from the Sun. At this distance, the planet receives about 260 times more energy per square meter than Earth receives from the Sun. It's like being perpetually bathed in the heat of hundreds of suns simultaneously. The gravitational relationship between the planet and star at this close distance creates incredible tidal forces. These forces are so strong that they've locked the planet's rotation to its orbital period, a phenomenon called tidal locking. This means the same hemisphere of the planet always faces the star, just as the same side of the Moon always faces Earth. However, the tidal forces on HD 189733b are far more extreme than anything we see in the Earth-Moon system. The 2.2-day orbital period creates conditions unlike anything we see in our solar system. Every 53 hours, this massive world completes an entire journey around its star. That means, if you could somehow stand on the surface of this gas giant, you would see the star rise and set every 26.5 hours. But only if you were in the twilight zone between the day and night sides of the planet. The tidal locking creates a permanent temperature differential that drives some of the most extreme weather patterns we've ever observed. The day side is continuously scorched by stellar radiation, reaching temperatures that can melt copper and bronze. Meanwhile, the night side, locked in eternal darkness, remains relatively cooler, though still hot enough to melt lead. This temperature difference creates pressure gradients that drive winds of unimaginable violence across the planet's surface. The discovery of HD 189733b was part of a revolution in exoplanet science that began in the mid-1990s, when the first hot Jupiter, 51 Pegasi b, was discovered in 1995 by Michel Mayor and Didier Queloz. It completely overturned our theories about planetary formation. We thought all gas giants would be found in the cold outer regions of star systems, like Jupiter and Saturn in our own solar system. The existence of these close-orbiting gas giants forced us to completely rethink how planets form and migrate within stellar systems. The scientific impact of discovering hot Jupiters like HD 189733b extends far beyond just cataloguing new worlds. These planets serve as natural laboratories for studying physics under extreme conditions that we simply cannot replicate on Earth or anywhere else in our solar system. They help us understand how atmospheres behave under intense stellar irradiation, how planetary magnetic fields interact with stellar winds, and how gravitational forces shape the evolution of planetary systems. What makes HD 189733b particularly valuable for scientific study is its brightness and the characteristics of its parent star. The star is relatively bright as seen from Earth, with a visual magnitude of 7.7, making it an ideal target for detailed spectroscopic analysis. While not visible to the naked eye, it's easily observable with modest telescopes and extremely accessible to professional astronomical instruments. This brightness has allowed astronomers to study the planet's atmosphere in unprecedented detail using a technique called transmission spectroscopy. When the planet transits its star, some of the star's light passes through the planet's atmosphere before reaching Earth. Different atmospheric compounds absorb light at specific wavelengths, creating a kind of fingerprint that reveals the chemical composition of the planet's atmosphere. It's like analyzing the atmosphere of a world over 60 light-years away by studying the shadows it casts in starlight. The planet's size and orbital characteristics also make it perfect for transit observations. When it passes in front of its star, it blocks about 2.4% of the star's light. This might not sound like much, but it's easily detectable with modern instruments and provides a wealth of information about the planet's atmosphere, size, and composition. The relatively large size of the planet compared to its star makes these measurements much more precise than they would be for smaller planets. Since its initial discovery, HD 189733b has become one of the most studied exoplanets in existence. It's been observed by virtually every major space telescope, from Hubble to Spitzer to Kepler, and now the James Webb Space Telescope. Each observation has revealed new details about this extraordinary world and its extreme atmospheric conditions. The planet has been featured in hundreds of scientific papers and has become a benchmark system for testing theories about exoplanet atmospheres. The wealth of observational data available for HD 189733b has made it a cornerstone of comparative planetology. By studying how this world differs from planets in our own solar system, scientists gain insights into the full range of possible planetary environments and atmospheric behaviors. This comparative approach helps us understand what makes Earth special, while also preparing us for the incredible diversity of worlds we're likely to encounter as our planet hunting techniques improve. The planet serves as a natural laboratory for studying atmospheric physics under conditions that simply don't exist anywhere in our solar system. Its extreme proximity to its star, its rapid orbital period, and its substantial mass create a perfect storm of conditions that generate some of the most violent weather patterns we've ever observed on any world. This makes it an invaluable target for understanding not just exoplanet atmospheres, but atmospheric dynamics in general. Perhaps most importantly, HD 189733b represents our first detailed look at truly alien weather. While we can study the atmospheres of planets and moons in our own solar system, they all formed under similar conditions and orbit the same star. This distant world shows us what's possible when you change the fundamental parameters of planetary formation and evolution. It's a glimpse into the incredible creativity of nature and the vast range of environments that exist throughout our galaxy. As we'll explore in the coming chapters, this seemingly simple gas giant orbiting a distant star holds secrets that have revolutionized our understanding of planetary weather, atmospheric chemistry, and the incredible diversity of worlds that exist throughout our galaxy. From its sideways rain of molten glass to its supersonic winds, HD 189733b continues to surprise and educate us about the extreme physics that govern alien worlds. To understand the hellish conditions on HD 189733b, we need to dive deep into the fundamental physics that creates one of the most extreme atmospheric environments we've ever discovered. The planet's proximity to its host star isn't just close, it's so extraordinarily close that it experiences conditions that push the very limits of what we consider possible for a stable planetary atmosphere. The host star, HD 189733, is classified as a K-type orange dwarf star, slightly smaller and cooler than our Sun. With a surface temperature of approximately 4,800 degrees Kelvin, it might seem less threatening than our Sun's 5,780 degree surface. However, when you're orbiting at a distance of just 4.6 million kilometers, the difference in stellar temperature becomes almost irrelevant. The sheer proximity more than compensates for the star's relatively cooler nature. At this incredibly close distance, HD 189733b receives an amount of energy that's difficult to comprehend. The planet absorbs approximately 260 times more energy per square meter than Earth receives from the Sun. To put this in perspective, imagine taking Earth and moving it to a position where it receives the combined energy output of 260 suns simultaneously. The dayside temperatures soar to approximately 1,300 degrees Celsius, hot enough to melt copper, bronze, and many other metals that we consider robust materials on Earth. But temperature alone doesn't tell the complete story of this world's atmospheric extremes. The real driver of the planet's violent weather is the dramatic temperature contrast created by tidal locking. Like our moon always showing the same face to Earth, HD 189733b is gravitationally locked to its star, with one hemisphere permanently facing the stellar furnace, while the other remains in eternal darkness. This tidal locking creates what atmospheric scientists call the most extreme temperature gradient known to exist on any planet. The day side, continuously baked by stellar radiation, maintains temperatures around 1,300 degrees Celsius. Meanwhile, the night side, forever shielded from the star's energy, cools to approximately 900 degrees Celsius, While 900 degrees might still seem incredibly hot by Earth standards, in the context of this world, it represents a temperature difference of 400 degrees Celsius across the planet's surface. This 400-degree temperature differential creates pressure gradients that are absolutely staggering in their intensity. Hot air on the day side expands and rises, creating massive low-pressure systems, while the relatively cooler air on the night side contracts and sinks, forming high-pressure zones. The pressure difference between these regions drives atmospheric circulation patterns that make Earth's most violent storms look like gentle breezes. The physics of heat distribution on tidally locked planets creates a phenomenon that atmospheric scientists call the hotspot offset. You might expect the hottest point on the planet to be at the substellar point, the location where the star appears directly overhead. However, atmospheric circulation patterns actually shift this hotspot eastward, in the direction of the planet's rotation. This offset occurs because the intense winds redistribute heat around the planet faster than the surface can radiate it away to space. The atmospheric composition of HD 189733b adds another layer of complexity to its extreme weather systems. Unlike Earth's atmosphere, which is dominated by nitrogen and oxygen, this hot Jupiter's atmosphere is primarily composed of hydrogen and helium, similar to Jupiter's atmosphere, but under vastly different temperature and pressure conditions. The extreme heat breaks down complex molecules that would normally exist in gas giant atmospheres, creating a chemical environment that's both alien and violent. At the temperatures present on HD 189733b, many compounds that we think of as solid materials become vaporized and enter the gas phase. Silicon dioxide, the primary component of glass and sand, vaporizes at temperatures around 1700 degrees Celsius. While the planet's average temperature is below this threshold, the hottest regions of the day side easily reach temperatures sufficient to vaporize silicate minerals. These vaporized silicates become incorporated into the planet's atmospheric circulation, creating clouds of gaseous rock that get transported around the planet by the extreme winds. As these silicate-rich air masses move toward the cooler night side, they encounter temperatures low enough for the silicon dioxide to condense back into solid particles. However, instead of falling straight down as precipitation, these newly formed glass droplets get caught up in the planet's supersonic wind systems. The atmospheric pressure on HD 189733b is another crucial factor in understanding its extreme weather. While we don't have precise measurements of the surface pressure, models suggest it could be dozens of times higher than Earth's atmospheric pressure at sea level. This high-pressure environment affects how heat is transported through the atmosphere and influences the behavior of the vaporized materials that create the planet's exotic clouds. The high pressure also affects the planet's atmospheric scale height, which is the altitude over which atmospheric pressure drops by a factor of approximately 2.7. On Earth, this scale height is about 8 kilometers, meaning that atmospheric pressure decreases significantly as you climb mountains or fly in aircraft. On HD 189733b, the combination of high temperature, high pressure, and the planet's strong gravitational field creates a much more compressed atmosphere where pressure changes more slowly with altitude. The planet's magnetic field, or lack thereof, also plays a crucial role in shaping its atmospheric environment. Unlike Earth, which has a strong magnetic field that protects our atmosphere from the solar wind, HD 189733b orbits so close to its star that any magnetic field it might have is likely overwhelmed by the intense stellar radiation and particle bombardment it experiences. This close proximity to the star means that the planet exists within what astronomers call the stellar magnetosphere, the region where the star's magnetic field dominates. The interaction between the planet's atmosphere and the star's magnetic field creates complex electromagnetic effects that can influence atmospheric dynamics and may contribute to the extreme wind speeds observed on the planet. The stellar wind from HD 189733 also plays a significant role in shaping the planet's atmosphere. stellar winds are streams of charged particles flowing away from stars, similar to, but much more intense than the solar wind that affects planets in our own solar system. At the close distance where HD 189733b orbits, this stellar wind is incredibly dense and energetic. The constant bombardment by stellar wind particles heats the upper atmosphere of the planet to even higher temperatures than the lower atmosphere experiences from stellar radiation alone. This creates a temperature inversion where the upper atmosphere is actually hotter than the lower atmosphere, a condition that's extremely rare in planetary atmospheres, but common among hot Jupiters. This temperature inversion has profound effects on atmospheric circulation. Normally, atmospheric convection occurs when hot air rises and cool air sinks. But when the upper atmosphere is hotter than the lower atmosphere, this normal convection pattern gets disrupted, creating complex three-dimensional flow patterns that contribute to the planet's extreme weather. The intense stellar radiation also drives atmospheric escape, where the lightest atmospheric components gain enough energy to escape the planet's gravitational pull entirely. For HD 189733b, this means that hydrogen, the lightest and most abundant atmospheric component, is constantly being stripped away from the planet and lost to space. This atmospheric loss creates a comet-like tail of escaping hydrogen that extends millions of kilometers behind the planet in its orbit. The rate of atmospheric escape on HD 189733b is truly staggering. Observations with the Hubble Space Telescope have detected hydrogen escaping from the planet at a rate of approximately 10,000 tons per second. To put this in perspective, that's equivalent to losing the mass of a small mountain every single day. While this might seem like it would quickly strip away the planet's entire atmosphere, the planet is so massive that it can sustain this loss rate for billions of years without significantly changing its overall atmospheric mass. The escaping hydrogen creates what astronomers call an extended hydrogen envelope around the planet. This envelope is much larger than the planet itself and can be detected when the planet transits its star, because the escaping hydrogen absorbs specific wavelengths of stellar light. These observations have provided unprecedented insights into the atmospheric escape process and how close orbiting planets interact with their host stars. The extreme temperatures and pressures on HD 189733b also affect the planet's atmospheric chemistry in ways that create conditions unlike anything we see in our solar system. The high temperatures break apart complex hydrocarbon molecules that would normally exist in gas giant atmospheres, while also enabling chemical reactions that would be impossible at lower temperatures. One of the most significant chemical effects is the thermal dissociation of molecular hydrogen. At the extreme temperatures present on the day side, some of the H2 molecules in the atmosphere break apart into individual hydrogen atoms. This dissociation absorbs enormous amounts of energy and affects how heat is transported through the atmosphere. When the dissociated hydrogen atoms recombine on the cooler night side, they release that energy back into the atmosphere, creating an additional heat transport mechanism that contributes to the planet's extreme winds. The atmospheric dynamics of HD 189733b are further complicated by what atmospheric scientists call the Coriolis effect, but amplified to an extreme degree. The Coriolis effect is the apparent deflection of moving objects caused by the rotation of the planet. On Earth, this effect is relatively weak because our planet rotates slowly, completing one rotation every 24 hours. But HD 189733b rotates much faster, completing one rotation every 2.2 days, which dramatically amplifies the Coriolis forces acting on atmospheric movements. These enhanced Coriolis forces interact with the extreme temperature gradients to create atmospheric circulation patterns that are fundamentally different from anything we observe on planets in our solar system. The combination of rapid rotation, extreme temperature differences, and high atmospheric pressure creates a perfect storm of conditions that generate the supersonic winds we'll explore in detail in the next chapter. The vertical structure of the planet's atmosphere adds yet another dimension to its complexity. Unlike Earth's atmosphere, which has distinct layers like the troposphere, stratosphere, and thermosphere, HD 189733b's atmosphere is more uniform in temperature with altitude due to the intense stellar heating. This creates what atmospheric scientists call an isothermal atmosphere, where temperature remains relatively constant from the bottom to the top of the atmospheric column. This isothermal structure has profound implications for atmospheric circulation. Without the temperature gradients that normally exist between different atmospheric layers, the usual mechanisms that create atmospheric stability are absent. This contributes to the violent turbulence and extreme wind speeds that characterize this world's weather systems. The combination of all these factors, the extreme stellar heating, the dramatic day-night temperature contrast, the high atmospheric pressure, the rapid rotation, the tidal locking, the atmospheric escape, and the complex chemistry, creates an atmospheric environment that represents the absolute extreme of what's possible for a planetary atmosphere. It's a world where the fundamental processes that govern atmospheric behavior are pushed to their absolute limits, creating weather patterns that are both fascinating and terrifying in their intensity. Understanding these extreme conditions isn't just an academic exercise. HD 189733b serves as a natural laboratory for studying atmospheric physics under conditions that we could never recreate on Earth. The insights gained from studying this world help us understand the full range of possible atmospheric behaviors and prepare us for the incredible diversity of conditions we're likely to encounter on other exoplanets as our observational capabilities continue to improve. The winds on HD 189733b represent one of the most extreme meteorological phenomena ever discovered in the universe. When astronomers first measured wind speeds reaching 8,700 kilometers per hour, or about 5,400 miles per hour, they initially questioned their instruments. These velocities seemed impossible, defying everything we understood about atmospheric dynamics. Yet multiple independent observations confirmed what seemed unthinkable. This distant world hosts winds that move faster than the speed of sound. To truly grasp the magnitude of these supersonic winds, we need to put them in the context of wind speeds we're familiar with on Earth. The strongest winds ever recorded in Earth's atmosphere occurred during Tropical Cyclone Olivia in 1996, when researchers measured a gust of 408 kilometers per hour on Barrow Island off the coast of Australia. The most powerful tornadoes on Earth generate winds that can reach 500 kilometers per hour in their most intense moments. Hurricane Katrina, one of the most destructive storms in recorded history, had sustained winds of only 175 kilometers per hour. Now imagine winds that are 50 times more powerful than Hurricane Katrina. Winds so violent that they make our most devastating tornadoes look like gentle summer breezes. Winds moving at velocities that exceed the speed of sound itself, creating shock waves that propagate through the atmosphere like the sonic booms of supersonic aircraft, but on a planetary scale. This is the reality of HD 189733b's atmospheric circulation. The discovery of these extreme wind speeds came through a sophisticated observational technique called Doppler spectroscopy, the same method used to detect the planet's initial orbital motion around its star. However, instead of measuring the star's motion, astronomers focused on the planet's atmosphere during transit events. When HD 189733b passes in front of its star, some of the star's light passes through the planet's atmosphere before reaching Earth. This transmitted light carries the spectral fingerprints of the atmospheric gases, but with a crucial twist. The motion of these gases creates Doppler shifts in the spectral lines. The Hubble Space Telescope played a crucial role in these wind speed measurements, using its high-resolution spectrographs to detect tiny wavelength shifts in sodium absorption lines passing through the planet's atmosphere, the high-accuracy radial velocity. Planet Searcher, or HARP's ground-based spectrograph, also contributed crucial data by measuring how atmospheric gases move relative to the planet's overall orbital motion. These observations required extraordinary precision, measuring velocity changes smaller than the speed of a walking person, while observing a planet over 60 light-years away. What makes these measurements even more remarkable is that astronomers can actually map the three-dimensional structure of the wind flow around the planet. By observing multiple transits and analyzing how the Doppler shifts change, as different parts of the atmosphere pass in front of the star, scientists have been able to create detailed maps showing how wind speed and direction vary across the planet's surface and at different altitudes in the atmosphere. The fundamental driver of these supersonic winds is the extreme temperature gradient we discussed in the previous chapter. But the mechanism by which temperature differences generate such extreme velocities involves some of the most complex atmospheric physics ever observed. The 400 degrees Celsius temperature difference between the day and night sides creates pressure gradients that are absolutely enormous compared to anything we experience on Earth. On Earth, pressure differences of just a few millibars are sufficient to generate significant weather systems. A typical low-pressure system might have a central pressure that's 10 to 20 millibars lower than the surrounding high-pressure areas. And this modest difference is enough to create storms with wind speeds of 100 kilometers per hour or more. On HD 189733b, the pressure differences are orders of magnitude larger, creating pressure gradients that accelerate atmospheric gases to velocities that seem impossible by terrestrial standards. The physics of how these pressure gradients accelerate atmospheric gases involves the fundamental relationship between pressure, temperature, and gas motion described by the laws of thermodynamics. When air is heated on the day side of the planet, it expands dramatically, creating regions of low pressure. This hot, expanded air then rushes toward the cooler, higher pressure regions on the night side. However, the planet's rapid rotation and strong Coriolis forces deflect this moving air, creating the complex circulation patterns that generate the observed wind speeds. The role of the Coriolis effect in shaping these winds cannot be overstated. On Earth, the Coriolis effect is relatively weak because our planet rotates slowly, taking 24 hours to complete one rotation. This creates the familiar pattern of cyclonic and anticyclonic circulation that we see in weather systems like hurricanes and typhoons. On HD 189733b, which rotates every 2.2 days, the Coriolis forces are much stronger, creating circulation patterns that are fundamentally different from terrestrial weather systems. These enhanced Coriolis forces create what atmospheric scientists call superrotation, where the atmosphere moves faster than the planet's surface rotates. This phenomenon is observed on Venus, where atmospheric winds reach 400 kilometers per hour, despite the planet's incredibly slow rotation period of 243 Earth days. However, the superrotation on HD 189733b is far more extreme than anything observed on Venus or any other planet in our solar system. The atmospheric circulation pattern on HD 189733b creates a phenomenon that scientists call an equatorial jet stream, but one that dwarfs any jet stream found on Earth. Our planet's jet streams typically reach maximum velocities of around 300 kilometers per hour and are confined to relatively narrow bands in the atmosphere. The equatorial jet on HD 189733b extends around the entire planet and reaches velocities that are nearly 30 times faster than Earth's most powerful jet streams. This planetary-scale jet stream is driven by the continuous flow of heated air from the day side toward the night side, but deflected by Coriolis forces into a predominantly east-west circulation pattern. The result is a river of supersonic gas flowing around the planet's equator, carrying with it all the exotic materials that vaporize in the extreme heat of the dayside atmosphere. The vertical structure of these winds adds another dimension to their complexity. Unlike Earth's atmosphere, where wind speeds generally decrease with altitude, the winds on HD 189733b appear to maintain their extreme velocities throughout much of the atmospheric column. This occurs because the entire atmosphere is heated nearly uniformly by the intense stellar radiation, eliminating the temperature gradients with altitude that normally slow down high-altitude winds on terrestrial planets. The interaction between these supersonic winds and the planet's atmospheric composition creates some of the most exotic weather phenomena ever observed. As we discussed in previous chapters, the extreme temperatures on the dayside vaporize silicate minerals, creating clouds of gaseous rock. These silicate vapors get caught up in the supersonic wind streams and transported around the planet at incredible velocities. When these silicate-laden air masses encounter the cooler temperatures on the night side, the vaporized minerals begin to condense back into solid particles. However, instead of forming the gentle precipitation we're familiar with on Earth, these condensing silicates create what can only be described as supersonic hail. Glass-like particles form in the atmosphere and are immediately accelerated to thousands of kilometers per hour by the surrounding wind field. The physics of particle motion in these extreme winds is governed by the same principles that affect objects in supersonic airflow, such as the shock waves that form around supersonic aircraft. When solid particles move through gas at supersonic speeds, they create bow shocks, compression waves that propagate ahead of the particle and dramatically affect the surrounding airflow. On HD 189733b, billions of these microscopic shock waves create a continuously turbulent atmosphere where the normal rules of fluid dynamics break down. The energy contained in these supersonic winds is truly staggering when calculated on a planetary scale. The kinetic energy of the moving atmosphere on HD 189733b is estimated to be equivalent to the energy output of thousands of nuclear power plants operating continuously. This energy is constantly being replenished by the stellar heating on the day side and dissipated through various mechanisms on the night side, creating a planetary scale heat engine that operates at efficiencies that would be impossible to achieve with any human technology. The turbulence generated by these supersonic winds creates atmospheric mixing on a scale that's difficult to comprehend. On Earth, it can take weeks or months for atmospheric disturbances to propagate around the planet. On HD 189733b, the supersonic winds can transport atmospheric components from the day side to the night side in a matter of hours, creating a level of atmospheric mixing that's unprecedented in our solar system. This rapid mixing has profound implications for the planet's atmospheric chemistry. Compounds that form on the hot day side can be transported to the cool night side before they have time to reach chemical equilibrium, creating a constantly evolving atmospheric composition that varies dramatically with location and time. The result is an atmosphere that's in a constant state of chemical disequilibrium, with reaction products being transported away from their formation sites before chemical reactions can reach completion. The supersonic winds also affect the planet's interaction with its host star's magnetic field and stellar wind. The rapid motion of ionized gases in the planet's upper atmosphere creates electrical currents that interact with the stellar magnetic field, generating electromagnetic effects that can influence both the planet's atmospheric dynamics and the star's own magnetic environment. These magneto-hydrodynamic interactions add yet another layer of complexity to the planet's already extreme atmospheric behavior. The observational evidence for these supersonic winds comes from multiple independent sources, each providing a different piece of the puzzle. Hubble Space Telescope observations have detected the motion of atmospheric gases through Doppler shifts in spectral lines. The Spitzer Space Telescope has measured how the planet's thermal emission varies as different parts of the atmosphere rotate into and out of view, providing evidence for the rapid transport of heat around the planet. Ground-based observations with instruments like HARPS have confirmed these measurements with even higher precision. Perhaps most remarkably, astronomers have been able to observe how these wind speeds change over time. Multiple observations spanning several years have shown that the wind patterns on HD 189733b are not constant, but exhibit variations that may be related to changes in the stellar activity of the host star. This suggests that the planet's atmospheric circulation is sensitive to external forcing from stellar variability, adding yet another layer of complexity to an already incredibly dynamic system. The study of these supersonic winds has revolutionized our understanding of atmospheric dynamics under extreme conditions. Prior to the discovery of HD 189733b, atmospheric scientists had no observational data for how atmospheres behave under such extreme heating and pressure gradients. The planet serves as a natural wind tunnel where we can study supersonic gas dynamics on a planetary scale, providing insights that are relevant not just for exoplanet science, but for fundamental fluid dynamics and atmospheric physics. These observations have also forced atmospheric scientists to develop new theoretical models and computational techniques for simulating atmospheric behavior under extreme conditions. Traditional atmospheric models, designed for the relatively mild conditions found on planets in our solar system, completely break down when applied to the extreme environment of HD 189733b. New models must account for supersonic flow effects, shockwave formation, and the complex three-dimensional interactions between temperature, pressure, rotation, and magnetic fields. The supersonic winds of HD 189733b represent just one aspect of this world's extreme weather, but they provide the driving force for many of the other exotic phenomena we observe. In the next chapter, we'll explore how these incredible wind speeds interact with the vaporized silicate materials in the atmosphere to create one of the most alien weather phenomena ever discovered: sideways rain made of molten glass. The most alien and terrifying aspect of HD 189733b's weather system is undoubtedly its rain of molten glass. This isn't a metaphor or a poetic description, it's a literal precipitation of liquid silicate droplets moving sideways through the atmosphere at thousands of kilometers per hour. To understand how such an impossible-sounding phenomenon can occur, we need to dive deep into the complex physics of high-temperature atmospheric chemistry and the behavior of vaporized minerals in extreme environments. The story of glass rain begins with the fundamental building blocks of rocky planets, silicate minerals. On Earth, these minerals form the backbone of our continents, existing as solid crystals in rocks like granite, basalt, and sandstone. Silicon dioxide, commonly known as quartz, is one of the most abundant minerals on Earth's surface and forms the primary component of ordinary glass. Under normal terrestrial conditions, these silicate minerals are stable solids with melting points that range from 1000 to 2000 degrees Celsius. However, the conditions on HD 189733b are anything but normal. With dayside temperatures reaching 1300 degrees Celsius, the planet exists in a thermal environment where many of the minerals that form solid rocks on Earth become vaporized gases. Silicon dioxide, the primary component of glass, has a boiling point of approximately 2230 degrees Celsius under standard atmospheric pressure. While the surface temperatures on HD 189733b don't quite reach this extreme, the combination of high temperature and the planet's intense atmospheric dynamics creates conditions where silicate vaporization becomes not just possible, but inevitable. The process begins in the superheated atmosphere above the planet's day side. Here, in the uppermost layers of the atmosphere where stellar radiation is most intense, temperatures can exceed even the average surface temperature. These extreme thermal conditions provide sufficient energy to break apart silicate minerals that may have formed earlier in the planet's atmospheric evolution, or that originate from meteoritic debris constantly raining down on the planet from space. When silicate minerals are heated to these extreme temperatures, they don't simply melt as they would on Earth. Instead, they undergo a process called thermal dissociation, where the chemical bonds holding the mineral structure together are broken by the intense thermal energy. Silicon dioxide molecules decompose into their constituent silicon and oxygen atoms, which then exist as free atoms and simple molecules in the gas phase. This process creates what atmospheric chemists call a silicate vapor phase, where atoms and molecules that normally exist only in solid rocks become dispersed throughout the planet's atmosphere, like any other atmospheric gas. The concentration of these vaporized silicates in the atmosphere depends on several factors: the availability of source material, the temperature and pressure conditions, and the atmospheric circulation patterns that transport these vapors around the planet. The supersonic winds we discussed in the previous chapter play a crucial role in the silicate rain formation process. These incredibly fast-moving air masses act like atmospheric conveyor belts, rapidly transporting the silicate-rich vapors from the superheated day side toward the relatively cooler night side. This transport happens so quickly that the vaporized silicates don't have time to reach chemical equilibrium before encountering dramatically different temperature and pressure conditions. As these silicate-laden air masses are carried by the supersonic winds toward the night side, they encounter a temperature gradient that's unlike anything found in nature on Earth. The temperature drops from 1,300 degrees Celsius on the day side to approximately 900 degrees Celsius on the night side, over a distance of just a few thousand kilometers. This represents a cooling rate that's orders of magnitude faster than any natural process on our planet. When the silicate vapors encounter these cooler temperatures, they begin to undergo the reverse of the thermal dissociation process that created them. Silicon and oxygen atoms start to recombine, forming silicon dioxide molecules and eventually larger molecular clusters. This process, called nucleation, is similar to how water vapor forms cloud droplets in Earth's atmosphere, but occurring at temperatures that would instantly vaporize any water and involving materials that exist as solid rock under terrestrial conditions. The nucleation of silicate droplets in the atmosphere of HD 189733b follows the same basic physical principles that govern cloud formation on Earth, but under conditions that push these principles to their absolute limits. As silicon dioxide molecules cluster together, they form tiny seed particles that serve as condensation nuclei for further growth. Additional silicon dioxide molecules attach to these seed particles, gradually building up larger and larger droplets. However, unlike water droplets in Earth's clouds, these silicate droplets form at temperatures exceeding 900 degrees Celsius. This means they exist in a molten state from the moment they form, essentially creating droplets of liquid glass suspended in the planet's atmosphere. The surface tension and viscosity of these molten silicate droplets are dramatically different from those of water droplets, affecting how they behave as they move through the atmospheric environment. The composition of these glass droplets is likely quite complex, not consisting of pure silicon dioxide, but rather a mixture of various silicates minerals that were vaporized in the dayside atmosphere. Spectroscopic observations suggest the presence of magnesium silicates, aluminum silicates, and possibly iron-bearing silicate compounds. This creates glass droplets with compositions similar to naturally occurring volcanic glasses like obsidian, but forming in an atmospheric environment, rather than through volcanic processes. The size distribution of these glass droplets depends on the complex interplay between nucleation rates, growth rates, and the atmospheric dynamics that affect their formation and evolution. Computer models suggest that the droplets likely range in size from microscopic particles just a few micrometers across to larger droplets that could reach several millimeters in diameter. The largest droplets represent an enormous amount of thermal energy, containing enough heat to cause severe burns even at the relatively cool temperatures found on the night side. What makes this precipitation truly alien is that these glass droplets don't fall straight down under the influence of gravity as rain does on Earth. Instead, they're immediately caught up in the supersonic wind systems that dominate the planet's atmospheric circulation. The result is precipitation that moves horizontally rather than vertically, creating what can only be described as sideways rain of molten glass. The physics of how these glass droplets move through the supersonic wind environment involves some of the most complex fluid dynamics problems in atmospheric science. When a solid or liquid particle moves through a gas at supersonic speeds, it creates shock waves that dramatically affect both the particle's motion and the surrounding airflow. Each glass droplet becomes like a microscopic supersonic projectile, generating its own bow shock wave as it moves through the atmosphere. These shock waves interact with the shock waves from billions of other glass droplets, creating a continuously turbulent environment where the normal rules of fluid dynamics break down. The result is an atmosphere filled with intersecting shock waves, pressure discontinuities, and regions of extremely high temperature and pressure that form and dissipate on timescales of microseconds. The thermal properties of the glass droplets add another layer of complexity to their atmospheric behavior. Unlike water droplets, which can evaporate and condense relatively easily, glass droplets have much higher thermal inertia. This means they retain their heat for much longer periods, remaining molten even as they're transported into regions of the atmosphere where the ambient temperature would normally cause them to solidify. This thermal persistence has profound implications for the planet's atmospheric energy balance. The glass droplets act like tiny thermal batteries, absorbing enormous amounts of heat energy on the day side, and then slowly releasing that energy as they're transported around the planet. This creates an additional mechanism for heat transport that supplements the already extreme atmospheric circulation, further enhancing the planet's ability to redistribute thermal energy from day to night. The cooling and eventual solidification of these glass droplets creates yet another fascinating aspect of this alien weather system. As the droplets are carried further into the night side and continue to lose heat through radiation, they eventually cool below their solidification temperature and transform from liquid glass into solid glass particles. This transformation doesn't happen all at once, but occurs gradually, with the outer layers of each droplet solidifying first, while the interior remains molten. This creates glass particles with complex internal structures, potentially consisting of solid outer shells surrounding molten cores. The thermal stresses created by this differential cooling could cause the glass particles to crack or shatter, creating even smaller fragments that add to the already complex particle size distribution in the atmosphere. The interaction between these glass particles and the planet's atmospheric gases creates additional chemical complexity. At the extreme temperatures involved, the glass droplets can react with atmospheric hydrogen, creating silicon hydride compounds and other exotic chemical species that don't exist under terrestrial conditions. These reactions can alter the composition of both the glass particles and the surrounding atmosphere, creating a constantly evolving chemical environment. The optical properties of the glass rain contribute significantly to the planet's distinctive deep blue appearance that's visible from Earth-based telescopes. The microscopic glass particles scatter light in a process similar to Rayleigh scattering, which creates the blue color of Earth's sky. However, the much higher concentration of scattering particles and their different size distribution creates a much more intense blue coloration than anything observed in our solar system. This scattering effect also affects the planet's energy balance by reflecting some of the incoming stellar radiation back to space. The glass particles act like microscopic mirrors, reducing the amount of energy that reaches the planet's lower atmosphere. However, this cooling effect is more than offset by the greenhouse warming caused by the same particles trapping thermal radiation, trying to escape to space. The formation and behavior of glass rain on HD 189733b represents one of the most extreme examples of atmospheric chemistry and physics that we've discovered. The processes involved push the boundaries of our understanding of how atmospheres can behave under extreme conditions and provide insights into the incredible diversity of environments that can exist on planets throughout the universe. The study of this phenomenon has required the development of entirely new theoretical models and computational techniques. Traditional atmospheric chemistry models, designed for the relatively mild conditions found in our solar system, are completely inadequate for describing the extreme conditions where rock vaporizes and rains as molten glass. Scientists have had to develop new mathematical frameworks that can handle the complex interactions between high-temperature chemistry, supersonic fluid dynamics, and electromagnetic effects. Perhaps most remarkably, the glass rain on HD 189733b demonstrates that the boundary between geology and meteorology becomes blurred under extreme conditions. On Earth, we think of rocks and minerals as belonging to geology, while atmospheric phenomena like clouds and precipitation belong to meteorology. On this distant world, geological materials become atmospheric phenomena, creating weather patterns that incorporate processes we normally associate with volcanic activity or industrial glassmaking. The implications of understanding glass rain extend far beyond just this single planet. As we discover more hot Jupiters and other extreme exoplanets, we're finding that exotic precipitation involving vaporized minerals may be common throughout the universe. Some planets may experience iron rain, others might have clouds of vaporized titanium, and still others could have precipitation involving even more exotic materials. The glass rain of HD 189733b serves as a window into the incredible creativity of nature and the vast range of environments that exist throughout our galaxy. It's a reminder that the universe is filled with phenomena that stretch our imagination and challenge our understanding of what's possible in planetary science. In our next chapter, we'll explore how scientists were able to detect and study this alien precipitation from over 60 light-years away, using some of the most sophisticated observational techniques ever developed. The discovery that HD 189733b experiences sideways rain of molten glass represents one of the most remarkable detective stories in modern astronomy. How do you detect glass rain on a planet that's over 60 light-years away, so distant that even our most powerful telescopes can't directly image its surface? The answer lies in the ingenious application of spectroscopy, the science of analyzing light to understand the composition and behavior of distant objects. The story begins with one of the most fundamental tools in astronomy, the spectrum. When light from any source is spread out into its component colors using a prism or diffraction grating, it creates a spectrum that acts like a fingerprint, revealing the chemical composition and physical conditions of the light source. Every element and compound absorbs and emits light at very specific wavelengths, creating patterns of bright and dark lines that astronomers can use to identify what materials are present and how they're behaving. For HD 189733b, the key breakthrough came from understanding how the planet's deep blue color could be detected and analyzed from Earth. When astronomers first began studying this world with the Hubble Space Telescope, they noticed something unusual about how it appeared during different phases of its orbit. Unlike the rocky planets in our solar system, which appear relatively colorless when viewed from space, HD 189733b exhibited a distinctly blue appearance that was visible even from interstellar distances. The discovery of this blue coloration came through a technique called phase curve photometry, where astronomers measure how the brightness of the planet changes as it orbits its star and presents different phases to our view, similar to how we see different phases of the Moon. As HD 189733b moves around its orbit, different parts of its illuminated surface become visible from Earth, allowing astronomers to study how light reflects off different regions of the planet's atmosphere. What made these observations particularly revealing was that the blue color wasn't uniform across the planet's surface. The intensity of the blue coloration varied depending on which part of the planet was visible, suggesting that whatever was causing the blue color was distributed unevenly throughout the atmosphere. This spatial variation provided the first clue that the blue color was related to atmospheric processes rather than the planet's bulk composition. The breakthrough in understanding the cause of this blue coloration came from detailed spectroscopic analysis using both the Hubble Space Telescope and ground-based instruments. When astronomers examined the light from HD 189733b at high resolution, they discovered the spectral signatures of light scattering by very small particles suspended in the planet's atmosphere. This type of scattering, known as Rayleigh scattering, is the same physical process that makes Earth's sky appear blue. However, the intensity of the blue scattering on HD 189733b was far greater than anything observed in our solar system. The amount of scattering indicated the presence of an enormous number of microscopic particles distributed throughout the planet's atmosphere. The wavelength dependence of this scattering provided crucial information about the size and composition of these particles, suggesting they were much smaller than typical dust grains, but larger than individual molecules. The key evidence for the silicate composition of these scattering particles came from infrared spectroscopy, particularly observations made with the Spitzer Space Telescope. Infrared light is particularly useful for studying atmospheric composition because different molecules absorb infrared radiation at characteristic wavelengths. When astronomers analyzed the infrared spectrum of HD 189733b, they found absorption features that matched the spectral signatures of silicon dioxide and other silicate compounds. These infrared observations were particularly challenging because they required detecting the thermal emission from the planet itself, rather than just reflected starlight. The Spitzer Space Telescope was uniquely suited for this task because of its extreme sensitivity to infrared radiation and its ability to distinguish between the light coming from the star and the much fainter thermal emission from the planet. The evidence for the existence of silicate particles in the atmosphere became even stronger when astronomers discovered that the infrared emission from the planet varied significantly between the day and night sides. The day side showed strong evidence for gaseous silicates at high temperatures, while the night side showed signatures consistent with condensed silicate particles at lower temperatures. This spatial variation provided direct evidence for the condensation of vaporized silicates as atmospheric gases are transported from hot to cool regions of the planet. Perhaps the most convincing evidence for glass rain came from transmission spectroscopy observations made during planetary transits. When HD 189733b passes in front of its star, as seen from Earth, some of the star's light passes through the planet's atmosphere before reaching our telescopes. This transmitted light carries information about the atmospheric composition and the presence of suspended particles. During these transit observations, astronomers detected strong absorption features at wavelengths corresponding to silicate particles. More importantly, they found that these absorption features varied in strength depending on which part of the atmosphere was being probed during different phases of the transit. This variation indicated that the silicate particles were not uniformly distributed throughout the atmosphere, but were concentrated in certain regions, consistent with the formation and transport of condensed particles by atmospheric circulation. The detection of supersonic winds provided another crucial piece of evidence for the glass rain hypothesis. Using high-resolution spectroscopy, astronomers were able to measure Doppler shifts in spectral lines that indicated atmospheric gases moving at speeds of thousands of kilometers per hour. These wind speed measurements showed that any particles forming in the atmosphere would be immediately caught up in these extreme air currents, preventing them from falling straight down under gravity, and instead creating the sideways precipitation pattern that characterizes glass rain. The timing of these spectroscopic observations was critical for understanding the atmospheric dynamics. By making repeated observations over multiple orbits of the planet, astronomers were able to track how the spectral signatures of silicate particles changed over time. These temporal variations showed that the formation and transport of glass particles is an ongoing, dynamic process rather than a static atmospheric feature. Ground-based observations using instruments like the High-Accuracy Radial Velocity Planet Searcher, or HARPS, provided additional confirmation through extremely precise radial velocity measurements. These observations detected the gravitational wobble of the host star caused by the planet's orbit, but with sufficient precision to also detect secondary effects caused by atmospheric dynamics on the planet itself. The complex velocity patterns revealed by these measurements were consistent with the presence of rapidly moving atmospheric features, supporting the supersonic wind and glass rain models. The analysis of these observational data required the development of sophisticated computer models that could simulate the complex interactions between atmospheric circulation, silicate chemistry, and radiative transfer. These models had to account for the unusual conditions on HD 189733b, including the extreme temperatures, supersonic winds, and the presence of vaporized rock in the atmosphere. One of the most challenging aspects of confirming the glass rain hypothesis was ruling out alternative explanations for the observed spectral features. Astronomers had to carefully consider whether the blue coloration and infrared absorption could be caused by other atmospheric components, such as organic compounds, metallic particles, or exotic ice crystals. Through detailed comparison of observed spectra with laboratory measurements and theoretical calculations, researchers were able to eliminate these alternative explanations and confirm that silicate particles provided the best match for the observational data. The breakthrough in definitively confirming glass rain came from polarimetry observations, which measure how light becomes polarized as it interacts with atmospheric particles. Different types of particles create characteristic polarization signatures that can be distinguished from one another. When astronomers measured the polarization of light from HD 189733b, they found patterns that were uniquely consistent with spherical liquid droplets rather than solid crystalline particles or irregular dust grains. This polarimetric evidence was particularly important because it provided direct confirmation that the silicate particles exist as liquid droplets rather than solid crystals. This distinction was crucial for establishing that the planet experiences actual glass rain with molten silicate droplets rather than just atmospheric dust or solid particle clouds. The study of HD 189733b also benefited from comparative observations of other hot Jupiter exoplanets. By comparing the atmospheric properties of this planet with other similar worlds, astronomers were able to identify which features were unique to HD 189733b and which might be common to all hot Jupiters. These comparative studies showed that while many hot Jupiters exhibit evidence for high-altitude clouds, the specific combination of conditions that creates glass rain appears to be relatively rare. Recent observations with the James Webb Space Telescope have provided even more detailed information about the atmospheric composition and dynamics of HD 189733b. The unprecedented infrared sensitivity and spectral resolution of JWST have allowed astronomers to detect previously unobservable molecular species in the planet's atmosphere and to study the vertical distribution of different atmospheric components with much greater precision than ever before. These JWST observations have confirmed many of the earlier findings about glass rain, while also revealing new details about the process. For example, JWST has detected evidence for temperature and compositional variations at different altitudes in the atmosphere, showing how the condensation of silicate particles varies with height above the planet's surface. These vertical profiles provide crucial constraints for atmospheric models and help scientists understand the three-dimensional structure of the glass rain phenomenon. The observational techniques used to study HD 189733b have also been applied to other exoplanets, leading to the discovery of various exotic atmospheric phenomena on worlds throughout the galaxy. Some planets show evidence for iron rain, others for titanium oxide clouds, and still others for precipitation involving even more unusual materials. These discoveries have established that exotic precipitation is likely common on exoplanets with extreme atmospheric conditions. The detection and characterization of glass rain on HD 189733b represents a triumph of observational astronomy and atmospheric physics. It demonstrates how astronomers can use sophisticated spectroscopic techniques to study detailed atmospheric processes on planets that are dozens of light years away. The success of these observations has paved the way for even more ambitious studies of exoplanet atmospheres and has provided a roadmap for detecting and characterizing atmospheric phenomena on potentially habitable worlds around other stars. Perhaps most importantly, the observational evidence for glass rain has fundamentally changed our understanding of what kinds of weather systems are possible in the universe. It has shown that atmospheric processes can be far more extreme and exotic than anything we experience on Earth, while also demonstrating that these extreme processes follow the same fundamental physical laws that govern atmospheric behavior on our own planet. This combination of familiar physics operating under alien conditions provides a fascinating window into the incredible diversity of environments that exist throughout our galaxy. To truly grasp the alien nature of HD 189733b's weather systems, we need to compare them directly with the most extreme meteorological phenomena on our own planet. This comparison reveals not only how different conditions can be elsewhere in the universe, but also helps us appreciate both the remarkable diversity of weather patterns possible under different planetary conditions and the relatively gentle nature of even our most violent storms. Let's begin with temperature, the fundamental driver of all weather systems. The most extreme temperatures ever recorded on Earth's surface range from -89 degrees Celsius in Antarctica to 54 degrees Celsius in Death Valley. This gives Earth a total temperature range of about 143 degrees Celsius from the coldest to the hottest locations. In comparison, HD 189733b experiences a temperature difference of 400 degrees Celsius between its day and night sides, nearly 3 times Earth's entire temperature range, occurring across just half the planet's surface. Even more striking is the absolute temperature scale. The hottest temperature ever reliably recorded on Earth was 54 degrees Celsius in Death Valley, California. This temperature, while deadly to unprotected humans, is cooler than a typical hot summer day compared to the 900 degrees Celsius night side of HD 189733b. The coolest part of this alien world is still hot enough to melt lead, zinc, and aluminum, making it more than 16 times hotter than Earth's hottest day. The dayside temperature of 1,300 degrees Celsius is so extreme that it has no terrestrial equivalent. To find comparable temperatures on Earth, we have to look at artificial environments like industrial furnaces used for steel production, or the interior of active volcanic systems. Even the hottest volcanic lava typically reaches temperatures of only 1,000 to 1,200 degrees Celsius, meaning that simply standing on the day side of HD 189733b would expose you to temperatures comparable to swimming in molten rock. Wind speeds provide another dramatic comparison that illustrates the extreme nature of this alien world. Earth's most powerful winds occur in tornadoes, where rotating columns of air can reach speeds of up to 500 kilometers per hour in the most extreme cases. These tornadoes represent the absolute pinnacle of atmospheric violence on our planet, capable of destroying buildings, lifting vehicles, and reshaping entire landscapes in a matter of minutes. However, even the most devastating tornado on Earth produces winds that are less than 6% as fast as the routine atmospheric circulation on HD 189733b. The planet's supersonic winds, reaching 8,700 kilometers per hour, move at velocities that are nearly 18 times faster than our most violent tornadoes. To put this in perspective, these winds move faster than the Concorde supersonic airliner at cruising speed and approach the velocities achieved by military fighter jets at maximum performance. The comparison becomes even more stark when we consider the scale and duration of these wind systems. Earth's tornadoes, despite their incredible destructive power, are relatively small and short-lived phenomena. Most tornadoes have diameters measured in hundreds of meters and persist for only minutes to hours. In contrast, the supersonic winds on HD 189733b encompass the entire planet and blow continuously, 24 hours a day, for the billions of years of the planet's existence. Hurricane systems provide a better comparison for planetary scale wind patterns, but even here, the differences are enormous. The strongest hurricanes on Earth, such as Hurricane Allen in 1980 or Hurricane Camille in 1969, have produced sustained winds of up to 300 kilometers per hour. These storms are massive systems that can span hundreds of kilometers and persist for weeks, representing some of the most powerful weather phenomena on our planet. Yet even these monster hurricanes pale in comparison to the atmospheric circulation on HD 189733b. The alien planet's winds are nearly 30 times faster than the strongest hurricane winds ever recorded on Earth. Moreover, while hurricanes eventually dissipate as they move over land or cool water, the wind systems on HD 189733b are continuously powered by the extreme temperature difference between the day and night sides, ensuring they never weaken or dissipate. The precipitation systems on the two worlds represent perhaps the most dramatic difference in weather phenomena. Earth's precipitation occurs primarily as water in its various phases: liquid rain, solid snow and hail, and occasionally freezing rain or sleet. The most extreme precipitation on Earth might be large hailstones, which can reach sizes of several centimeters in diameter and fall at speeds of up to 150 kilometers per hour during severe thunderstorms. These terrestrial hailstones, dangerous as they can be, are composed of ordinary ice and fall under the influence of gravity in relatively predictable patterns. In contrast, the glass rain on HD 189733b consists of molten silicate droplets moving horizontally at thousands of kilometers per hour. A single glass droplet from this alien world, moving at these extreme velocities, would carry more kinetic energy than a high-powered rifle bullet. The composition of precipitation provides another fascinating point of comparison. On Earth, precipitation consists almost entirely of water, with occasional volcanic ash or dust mixed in during extreme events. The most exotic precipitation we experience might be colored rain caused by dust from distant deserts, or black rain containing volcanic particles. Even these unusual events involve materials that are fundamentally similar to ordinary terrestrial matter. The glass rain on HD 189733b represents precipitation of material that exists as solid rock under Earth conditions. Imagine if Earth's rain consisted of liquid granite or molten basalt instead of water. This gives us some sense of how alien the precipitation on this distant world truly is. The droplets falling sideways through its atmosphere are composed of the same silicon dioxide that forms beaches, desert sand, and window glass on Earth, but existing in a liquid state and moving at supersonic velocities. The energy scales involved in these weather systems also provide striking contrasts. Earth's most powerful hurricane might contain energy equivalent to several hundred nuclear weapons, representing an enormous concentration of atmospheric power. The kinetic energy of a major tornado, while more concentrated, is still relatively modest when calculated on a planetary scale. The continuous atmospheric circulation on HD 189733b contains energy that dwarfs even our most powerful storms. The kinetic energy of the planet's supersonic winds is estimated to be equivalent to thousands of continuously operating nuclear power plants. This energy is not concentrated in a small storm system that moves across the planet, but distributed throughout the entire atmospheric system and maintained constantly by the extreme temperature gradients. The atmospheric pressure differences that drive these contrasting weather systems also reveal the extreme nature of conditions on HD 189733b. On Earth, weather systems are driven by pressure differences that typically amount to just a few % of the total atmospheric pressure. A strong low-pressure system might have a central pressure that's only 10 to 20 millibars lower than the surrounding high-pressure areas, yet this small difference is sufficient to generate powerful storms. The pressure gradients on HD 189733b are estimated to be orders of magnitude larger than anything experienced on Earth. The extreme temperature differences between day and night sides create pressure variations that are not just percentages of the total atmospheric pressure, but represent fundamental differences in the atmospheric state. These extreme pressure gradients are what drive the supersonic winds that redistribute energy around the planet. The timescales of weather phenomena also differ dramatically between the two worlds. On Earth, weather systems typically evolve over periods of hours to weeks. A thunderstorm might develop and dissipate in a few hours, while a hurricane system can persist for days or weeks as it moves across the ocean. Seasonal weather patterns change over months, and long-term climate variations occur over years to decades. On HD 189733b, the fundamental weather patterns are determined by the planet's orbital and rotational characteristics, which remain constant over geological time periods. The basic circulation pattern, with hot day-side air flowing toward the cold night side and being deflected into supersonic winds by Coriolis forces, has likely remained unchanged for billions of years. While there may be shorter-term variations in wind speed or precipitation intensity, the overall weather system is locked into a pattern by the planet's extreme orbital configuration. The predictability of weather also differs dramatically between Earth and this alien world. Earth's weather is notoriously difficult to predict more than a few days in advance due to the chaotic nature of atmospheric dynamics and the complex interactions between multiple variables. Small changes in initial conditions can lead to dramatically different outcomes, making long-term weather forecasting extremely challenging. In contrast, the weather on HD 189733b is likely much more predictable, at least in its large-scale patterns. The extreme temperature gradients and rapid rotation create atmospheric circulation patterns that are dominated by the planet's fundamental physical characteristics, rather than subtle variations in initial conditions. While local variations might be difficult to predict, the overall pattern of supersonic winds and glass rain is probably quite stable and predictable over long time periods. The seasonal variations that characterize Earth's weather are completely absent on HD 189733b. Our planet's tilted rotation axis creates seasonal changes in solar heating that drive many of our weather patterns and create the annual cycles of temperature, precipitation, and storm activity that define climate in different regions. The tidally locked nature of HD 189733b means there are no seasonal variations, just the constant extreme temperature difference between the permanently hot day side and the permanently cooler night side. Perhaps most importantly, the comparison between Earth and HD 189733b highlights the narrow range of conditions that make our planet habitable. Earth's relatively gentle weather, while sometimes dangerous to human activities, operates within temperature and pressure ranges that allow liquid water to exist and complex chemistry to occur. The extreme conditions on the alien world would instantly destroy any form of life as we know it. This comparison also illustrates how the same fundamental physical laws that govern Earth's atmosphere can produce radically different outcomes under different planetary conditions. The principles of thermodynamics, fluid dynamics, and atmospheric chemistry that drive Earth's weather systems are the same ones operating on HD 189733b. However, the extreme temperature, pressure, and compositional conditions on the alien world push these physical processes into regimes that create weather patterns unlike anything in our solar system. Understanding these extreme weather systems helps us appreciate both the incredible diversity of atmospheric conditions possible throughout the universe and the special nature of Earth's relatively stable and gentle climate. It also provides crucial insights for understanding atmospheric processes under extreme conditions, knowledge that will be invaluable as we continue to discover and study the growing population of exoplanets orbiting stars throughout our galaxy. Imagine for a moment that you could somehow survive the journey to HD 189733b and attempt to explore this alien world. What would it be like to experience firsthand the most extreme weather system ever discovered? The reality is so hostile, so utterly destructive, that it challenges our ability to even conceive of materials or technologies that could withstand such conditions for more than a few seconds. Let's begin with the fundamental challenge of simply existing in an atmosphere where the air itself moves faster than the speed of sound. On Earth, we're accustomed to wind speeds that, even in the most extreme tornadoes, rarely exceed 500 kilometers per hour. At those velocities, ordinary objects become deadly projectiles, and the wind itself exerts forces that can lift cars and destroy buildings. Now imagine winds that are 18 times more powerful, moving at 8,700 kilometers per hour. At these supersonic velocities, the very concept of wind as we understand it breaks down. Instead of flowing air currents, you would experience atmospheric shock waves that propagate through the environment like continuous sonic booms. The pressure waves alone would be sufficient to crush any conventional structure instantaneously. The human body, evolved to function in Earth's gentle atmospheric conditions, would be destroyed in microseconds by forces that exceed anything we can comprehend from terrestrial experience. The temperature environment presents challenges that are equally insurmountable. Standing on the day side of HD 189733b would expose you to surface temperatures of 1,300 degrees Celsius, hot enough to melt copper, bronze, and many steel alloys. At these temperatures, most materials we consider heat-resistant would begin to soften, deform, and eventually melt. The soles of your boots would liquefy before you could take a single step, and any exposed metal components would begin glowing white hot within seconds. Even if you could somehow shelter from the direct stellar radiation on the relatively cooler night side, you would still face temperatures of 900 degrees Celsius, hot enough to melt zinc, aluminum, and lead. These temperatures are more than hot enough to ignite paper, wood, and most organic materials instantaneously. At these thermal conditions, the water in your body would flash to steam in milliseconds, and your cellular structure would be destroyed by thermal shock before you could even register the sensation of heat. The atmospheric pressure on HD 189733b adds another dimension to the hostile environment. While exact pressure measurements are difficult to obtain for such a distant world, atmospheric models suggest pressures that could be dozens of times higher than Earth's sea level pressure. This creates an environment where even breathing, if it were somehow possible, would be like trying to inhale liquid rather than gas. High-pressure environments affect human physiology in ways that are immediately life-threatening. The increased pressure would force gases into your bloodstream at rates that would cause fatal gas embolisms within seconds. Your lungs would be compressed beyond their ability to function, and the pressure differential between your internal body cavities and the external environment would cause catastrophic internal injuries. But perhaps the most alien and terrifying aspect of this environment would be the continuous bombardment by glass rain moving at supersonic velocities. Each molten silicate droplet, no larger than a raindrop on Earth, would impact with the kinetic energy of a high-powered rifle bullet. A single droplet striking any part of your body would create a wound comparable to a gunshot, instantly vaporizing flesh and bone at the point of impact. The density of this glass precipitation means you would be struck by thousands of these supersonic projectiles every second. It would be like standing in front of a machine gun that fires molten glass bullets continuously, with no possibility of shelter or protection. The cumulative effect would be total disintegration of any material object within seconds of exposure. The thermal properties of these glass droplets add an additional layer of destruction. Each droplet retains heat from its formation in the dayside atmosphere, carrying temperatures of hundreds of degrees Celsius even after being transported to the cooler night side. Upon impact, these droplets would not only cause physical trauma, but would also burn and cauterize tissue simultaneously, creating wounds that combine the worst aspects of ballistic injury and severe thermal burns. The optical environment on HD 189733b would be unlike anything experienced on Earth. The continuous presence of billions of microscopic glass particles in the atmosphere would create a scattering effect that makes the entire sky glow with an intense blue light. This isn't the gentle blue of Earth's sky, but a brilliant, almost electric blue that would be painful to look at directly, even if your eyes could somehow survive the other environmental hazards. The light scattering would also create optical phenomena that have no terrestrial equivalent. The supersonic motion of glass particles would create continuous flashes and sparkles as droplets reflect and refract starlight, creating a kind of cosmic fireworks display that never ends. However, the beauty of these optical effects would be completely overshadowed by their deadly nature, as each flash represents a supersonic glass projectile that could instantly destroy any technological device or biological organism. The electromagnetic environment presents additional challenges that would affect any electronic equipment you might bring to this alien world. The high temperature ionizes atmospheric gases, creating a partially ionized plasma environment that would interfere with radio communications and electronic systems. The rapid motion of charged particles in the supersonic winds would generate electromagnetic fields that could induce damaging electrical currents in any metallic objects. The constant bombardment by glass particles would also create electrical effects, as the high velocity impacts generate static charges and electromagnetic pulses. Any electronic device would be subjected to continuous electromagnetic interference, while simultaneously being physically destroyed by glass particle impacts, making technological survival impossible even for devices designed to operate in extreme environments. Consider the challenges of designing any kind of protective shelter or vehicle that could survive in this environment, even briefly. The structure would need to withstand continuous impacts from supersonic glass projectiles, while maintaining structural integrity at temperatures that exceed the melting points of most engineering materials. The shelter would also need to resist crushing by the extreme atmospheric pressures, while providing some means of temperature control in an environment where the outside temperature could melt the shelter walls. current materials, science offers no solutions to these challenges. The most heat-resistant ceramics, designed for spacecraft heat shields and industrial furnaces, begin to degrade at temperatures well below those routinely experienced on HD 189733b. Advanced refractory metals like tungsten and rhenium have among the highest melting points of any known materials, but even these would soften and lose their structural properties under the thermal conditions present on this alien world. The development of any material capable of surviving on HD 189733b would require advances in materials science that go far beyond our current technological capabilities. Such materials would need to combine extreme temperature resistance with the ability to withstand high-velocity impacts while maintaining structural integrity under crushing pressures. They would essentially need to be stronger and more heat-resistant than any material that has ever existed on Earth. Even if such miraculous materials could be developed, the engineering challenges of creating functional systems would be enormous. How do you design mechanical joints that can operate at temperatures that would melt conventional lubricants? How do you create seals that can maintain pressure differentials when the sealing materials would vaporize in the external environment? How do you provide cooling for internal systems when the external environment is hot enough to melt the cooling system itself? The energy requirements for maintaining any kind of habitable environment would be staggering. You would need to provide continuous cooling to keep internal temperatures below the melting point of your structural materials, while also maintaining pressure equilibrium with the crushing external atmosphere. The power requirements would exceed the capabilities of any portable energy system, and any external power generation equipment would be instantly destroyed by the environmental conditions. The psychological effects of experiencing such an environment, even from within a hypothetical protective shelter, would be beyond human comprehension. The continuous noise of supersonic winds and glass particle impacts would create a cacophony that exceeds the pain threshold for human hearing. The knowledge that you are surrounded by an environment so hostile that every cubic meter of air contains enough destructive force to instantly annihilate you would create levels of stress and anxiety that the human mind is not equipped to handle. The isolation from any familiar environmental cues would be profound. There would be no day-night cycle as we understand it, just the continuous extreme heat of the day side and the slightly less extreme heat of the night side. There would be no weather variations, no seasonal changes, no natural rhythms that connect to biological processes. The environment would be utterly alien and completely disconnected from any aspect of terrestrial experience. Perhaps most unsettling would be the realization that this hostile environment extends in every direction for thousands of kilometers, with no possibility of escape or relief. On Earth, even in the most extreme environments like the Antarctic or the deep ocean, there is always the knowledge that more hospitable conditions exist somewhere else on the planet. On HD 189733b, the entire world is equally hostile, with no refuge anywhere on the planetary surface. The glass storm environment of HD 189733b represents the absolute extreme of hostile planetary conditions. It's a world where the fundamental processes that sustain life and technology on Earth become impossible, where the very air would instantly destroy any object from our world, and where the environmental conditions push the laws of physics to create phenomena that have no parallel in human experience. Yet studying this impossible environment has profound value for understanding the diversity of conditions that exist throughout the universe. It expands our conception of what kinds of worlds are possible and helps us appreciate the remarkable hospitality of our own planet. It also drives the development of new technologies and materials that, while unable to survive on HD 189733b, may find applications in other extreme environments throughout our solar system and beyond. The glass storm world serves as a reminder that the universe contains environments so extreme that they challenge our imagination and push the boundaries of what we consider possible. It's a place where beauty and violence combine in ways that are both fascinating and terrifying, creating phenomena that exist nowhere else in our experience, but demonstrate the incredible creativity of nature operating under conditions that are as far from Earth like as we can imagine. Given the absolutely terrifying and utterly inhospitable conditions on HD 189733b, a reasonable question emerges. Why do scientists invest enormous amounts of time, money, and technological resources studying a world where no form of life could possibly survive, and no human technology could function for more than a few seconds? The answer reveals fundamental aspects of how scientific knowledge advances and why understanding extreme environments throughout the universe is crucial for our broader comprehension of planetary science, atmospheric physics, and our place in the cosmos. The study of extreme exoplanets like HD 189733b operates on the same principle that drives much of fundamental scientific research. Understanding nature at its limits reveals principles and processes that remain hidden under normal conditions. Just as physicists study matter at temperatures near absolute zero, or pressures that exist only in the cores of stars to understand fundamental physical laws, planetary scientists study worlds with extreme atmospheres to understand how atmospheric processes behave when pushed to their absolute limits. HD 189733b serves as a natural laboratory for studying atmospheric physics under conditions that we could never create or sustain on Earth. No terrestrial facility can reproduce the combination of extreme temperature gradients, supersonic wind speeds, and high-pressure silicate chemistry that characterizes this alien world. By studying how these processes operate under such extreme conditions, scientists gain insights into the fundamental physics of atmospheric dynamics that apply to all planetary atmospheres, including our own. Consider the advances in atmospheric modeling that have resulted from studying hot Jupiters like HD 189733b. Traditional atmospheric models, developed to understand Earth's relatively gentle climate, completely failed when applied to these extreme worlds. The temperature and pressure conditions were so far outside the range of terrestrial experience that entirely new mathematical frameworks had to be developed to describe atmospheric behavior under such conditions. These new modeling techniques have had profound impacts beyond just exoplanet science. The advanced computational methods developed to simulate supersonic atmospheric flows on hot Jupiters have found applications in studying extreme weather events on Earth, such as the atmospheric dynamics inside the most powerful hurricanes and tornadoes. The techniques used to model high-temperature atmospheric chemistry on alien worlds have improved our understanding of atmospheric processes in Earth's upper atmosphere and stratosphere. The study of glass rain on HD 189733b has revolutionized our understanding of cloud formation and precipitation processes under extreme conditions. Scientists have had to develop entirely new theories for how particles nucleate, grow, and interact in high-temperature, high-pressure environments. These theoretical advances have applications far beyond exoplanet science, contributing to our understanding of industrial processes, materials science, and even the formation of clouds in Earth's atmosphere under unusual conditions. The extreme atmospheric circulation patterns on HD 189733b have also provided crucial insights into fluid dynamics and magnetohydrodynamics that have broad applications across multiple scientific disciplines. The planet's supersonic winds operate in regimes where traditional fluid dynamics equations break down, requiring the development of new mathematical approaches that can handle shockwave formation, turbulence, and heat transfer under extreme conditions. These advances in fluid dynamics have found applications in aerospace engineering, where understanding supersonic flow is crucial for designing aircraft and spacecraft that operate at high velocities. The computational techniques developed to model atmospheric circulation on hot Jupiters have been adapted for studying airflow around supersonic aircraft, improving designs for next-generation hypersonic vehicles that may one day enable rapid travel anywhere on Earth or efficient transportation to other planets. The study of atmospheric escape on HD 189733b has provided fundamental insights into how planetary atmospheres evolve over geological timescales. The planet loses approximately 10,000 tons of hydrogen per second to space, creating a natural laboratory for studying the processes that determine whether planets can retain their atmospheres over billions of years. These insights are crucial for understanding the long-term habitability of planets throughout the universe. Understanding atmospheric escape has direct relevance for assessing the habitability of potentially Earth-like exoplanets. Many of the rocky planets discovered around nearby stars orbit much closer to their host stars than Earth orbits the Sun, subjecting them to intense stellar radiation that could strip away their atmospheres. The detailed studies of atmospheric escape on HD 189733b provide the theoretical framework and observational techniques needed to assess whether these potentially habitable worlds can actually retain the atmospheric conditions necessary for liquid water and life. The electromagnetic interactions between HD 189733b and its host star have also provided unprecedented insights into how planets interact with stellar magnetic fields and stellar winds. These interactions are fundamental to understanding how stellar activity affects planetary atmospheres and climate, with direct implications for the habitability of planets around different types of stars. Many of the potentially habitable exoplanets discovered by missions like Kepler and TESS orbit red dwarf stars, which are smaller and cooler than our Sun, but also much more magnetically active. These stars produce powerful stellar flares and intense stellar winds that could have dramatic effects on planetary atmospheres. The detailed studies of star-planet interactions using HD 189733b as a laboratory provide crucial insights into how these interactions might affect the habitability of planets around red dwarf stars. The spectroscopic techniques developed to study the atmosphere of HD 189733b have revolutionized the field of exoplanet atmospheric characterization. The methods used to detect wind speeds, atmospheric composition, and temperature structures on this extreme world have been adapted and refined for studying the atmospheres of potentially habitable planets. These techniques will be essential for determining whether any of the Earth-like worlds discovered around nearby stars actually have atmospheric conditions that could support life. The James Webb Space Telescope and other next-generation observatories will use many of the same spectroscopic methods first developed and tested on hot Jupiters like HD 189733b to search for signs of water vapor, oxygen, and other potential biosignature gases in the atmospheres of rocky exoplanets. The expertise gained from studying extreme atmospheric conditions provides the foundation for detecting and characterizing the subtle atmospheric signatures that might indicate the presence of life on distant worlds. HD 189733b also serves as a crucial test case for theoretical models of planetary formation and evolution. The existence of hot Jupiters was completely unexpected when the first exoplanets were discovered in the 1990s, forcing scientists to completely revise their understanding of how planetary systems form and evolve. The detailed study of these worlds has led to new theories of planetary migration, where gas giants form in the outer regions of stellar systems and then spiral inward due to gravitational interactions with the disk of gas and dust from which they formed. These new theories of planetary migration have profound implications for understanding the formation of our own solar system and predicting what kinds of planetary systems are likely to be common throughout the galaxy. The processes that create hot Jupiters, like HD 189733b, also influence the formation and evolution of smaller rocky planets. affecting whether terrestrial worlds end up in the habitable zones of their stellar systems or are ejected into interstellar space. The study of extreme worlds also provides crucial context for understanding Earth's climate system and its long-term stability. By studying how atmospheric processes behave under radically different conditions, scientists gain insights into the factors that have kept Earth's climate relatively stable over billions of years, and the potential vulnerabilities that could lead to dramatic climate changes in the future. The extreme greenhouse effects observed on hot Jupiters, while far more intense than anything possible on Earth, provide insights into the fundamental physics of how greenhouse gases interact with stellar radiation. These studies contribute to our understanding of climate sensitivity and the potential for runaway greenhouse effects, information that is crucial for predicting how Earth's climate might respond to changing atmospheric composition. From a technological perspective, the extreme conditions on HD 189733b drive advances in materials science and engineering that have applications far beyond space exploration. The need to develop instruments and spacecraft that can study such hostile environments pushes the boundaries of what's possible with current technology, leading to innovations that often find applications in terrestrial industries. The high temperature, high pressure conditions that characterize this alien world are similar to those found in many industrial processes, from steel production to chemical manufacturing. The theoretical understanding gained from studying how materials behave under the extreme conditions on HD 189733b contributes to the development of better industrial processes and more efficient manufacturing techniques. The study of extreme exoplanets also has profound philosophical and cultural implications. These worlds expand our conception of what kinds of environments are possible in the universe and challenge our assumptions about the conditions necessary for interesting planetary phenomena. They remind us that Earth represents just one point in an enormous range of possible planetary environments, helping us appreciate both the uniqueness of our world and the incredible diversity of conditions that exist throughout the galaxy. Perhaps most importantly, studying worlds like HD 189733b helps prepare us for the incredible diversity of environments we're likely to encounter as our space exploration capabilities advance. While we may never visit such an extreme world in person, the knowledge gained from studying it remotely will be invaluable for understanding and exploring other exotic environments throughout our solar system and beyond. The technological challenges of studying HD 189733b also drive the development of new observational techniques and instruments that will be essential for future space missions. The precision required to detect and characterize atmospheric processes on a planet over 60 light-years away pushes the limits of what's possible with current technology, leading to innovations in telescope design, detector technology, and data analysis techniques. These technological advances have applications that extend far beyond astronomy. The image processing techniques developed to extract atmospheric information from exoplanet observations have found applications in medical imaging, satellite remote sensing, and industrial quality control. The precision measurement techniques required to detect atmospheric gases on distant worlds contribute to advances in analytical chemistry and environmental monitoring on Earth. The study of HD 189733b ultimately represents humanity's quest to understand our place in the universe. By studying worlds that are as different from Earth as we can imagine, we gain perspective on the special characteristics that make our planet habitable and learn about the full range of environments that nature can create. This knowledge is essential for understanding whether life might exist elsewhere in the universe, and for appreciating the remarkable circumstances that have allowed life to flourish on our own world. The hostile glass storm world of HD 189733b may seem utterly alien and irrelevant to human concerns, but its study has contributed to advances in atmospheric science, fluid dynamics, materials science, planetary formation theory, and observational astronomy that benefit our understanding of countless other phenomena throughout the universe. It serves as a reminder that scientific knowledge is interconnected and that studying nature at its most extreme often reveals fundamental principles that apply across a wide range of conditions and environments. The discovery of glass rain on HD 1897333b raises a fascinating question that goes to the heart of understanding planetary diversity throughout our galaxy. Is this world a unique cosmic oddity, or does it represent just one example of a broader class of planets where exotic mineral precipitation occurs routinely? The answer to this question has profound implications for our understanding of planetary formation, atmospheric evolution, and the incredible range of environments that exist throughout the universe. To understand how common glass rain planets might be, we first need to consider the specific conditions that create this phenomenon. The glass rain on HD 1897333b results from a very particular combination of factors: extreme proximity to the host star, tidal locking that creates enormous temperature gradients, supersonic atmospheric circulation, and atmospheric compositions that include vaporizable silicate materials. Each of these conditions must be present simultaneously for glass rain to occur, which immediately suggests that such worlds might be relatively rare. However, as our census of exoplanets has grown from just a handful of known worlds in the 1990s to over 5,000 confirmed planets today, we've discovered that hot Jupiters like HD 1897333b are actually quite common throughout the galaxy. Current estimates suggest that between 1 and 5% of Sun-like stars host hot Jupiter planets, which may seem like a small percentage until you consider that there are hundreds of billions of stars in our galaxy alone. This means there could be millions or even tens of millions of hot Jupiter planets in our galaxy, each potentially experiencing some form of extreme atmospheric phenomena. While not all of these worlds will have exactly the same conditions as HD 1897333b, many of them likely experience similar processes involving the vaporization and condensation of refractory materials in their atmospheres. The key factor that determines whether a hot Jupiter experiences glass rain appears to be the atmospheric temperature profile and the availability of silicate materials. Planets that orbit very close to their stars, with day-side temperatures exceeding 1,000 degrees Celsius, are likely to have sufficient thermal energy to vaporize silicate minerals. When combined with the rapid atmospheric circulation typical of tidally locked worlds, these conditions create the perfect environment for glass rain formation. Recent surveys of hot Jupiter atmospheres have found evidence for high-altitude clouds and hazes on many of these worlds, suggesting that mineral condensation processes are indeed common among close orbiting gas giants. Observations of planets like WASP-17b, HAT-P7b, and Kepler-7b have revealed atmospheric features that are consistent with clouds composed of condensed minerals, though the specific composition and behavior of these clouds varies from planet to planet. WASP-17b, located approximately 1,000 light-years from Earth, shows spectroscopic evidence for clouds composed of aluminum oxide and titanium oxide particles. The aluminum oxide clouds on this world would create precipitation of microscopic sapphire and ruby particles, as these gemstones are simply crystalline forms of aluminum oxide. While not as exotic as glass rain, sapphire precipitation represents another example of how extreme atmospheric conditions can create weather phenomena that have no terrestrial equivalent. The study of HAT-P7b has revealed even more extreme atmospheric behavior, with evidence for clouds composed of vaporized metals, including iron and magnesium. On the day side of this world, metals exist as gases in the upper atmosphere, while on the night side they condense into metallic droplets that fall as liquid metal rain. This creates weather systems where it literally rains molten iron, with droplets of liquid metal moving through the atmosphere at thousands of kilometers per hour. Kepler 7b presents yet another variation on the theme of exotic precipitation, with observations suggesting the presence of silicate clouds similar to those on HD 189733b, but with different particle sizes and distribution patterns. The clouds on this world appear to be more uniform and less dynamic than the glass rain systems observed on HD 189733b, possibly due to differences in atmospheric circulation or stellar heating patterns. These discoveries suggest that exotic mineral precipitation may be the rule rather than the exception among hot Jupiter planets. Each world appears to have its own unique combination of atmospheric chemistry and dynamics that creates different types of mineral clouds and precipitation patterns. The specific type of exotic rain that occurs depends on factors such as the host star's temperature, the planet's atmospheric composition, and the detailed structure of atmospheric circulation patterns. The host star characteristics play a crucial role in determining what types of exotic precipitation can occur. Stars that are hotter than our Sun produce more intense ultraviolet radiation, which can break apart complex molecules in planetary atmospheres and create conditions favorable for metal vapor formation. Cooler stars may not provide sufficient energy to vaporize the most refractory materials, leading to different types of cloud composition and precipitation patterns. The metallicity of the host star, which refers to the abundance of elements heavier than hydrogen and helium, also influences the types of materials available for exotic precipitation. Stars with higher metallicity are more likely to host planets with atmospheres rich in silicon, aluminum, titanium, and other elements that can form exotic mineral clouds. Stars with lower metallicity may produce planets where exotic precipitation involves different materials or occurs under different conditions. Recent theoretical work has expanded our understanding of what types of exotic precipitation might be possible under different planetary conditions. Computer models of hot Jupiter atmospheres have predicted the existence of worlds where it rains liquid titanium, vaporized quartz, molten corundum, and even exotic compounds that don't exist naturally on Earth. These models suggest that the range of possible exotic precipitation types is limited mainly by the chemical elements available in planetary atmospheres and the temperature and pressure conditions that determine which materials can vaporize and condense. One particularly intriguing possibility is the existence of planets where multiple types of exotic precipitation occur simultaneously or in sequence. A planet with a complex atmospheric chemistry might experience glass rain in some regions while having iron rain in others, creating weather systems of incredible complexity and diversity. The atmospheric circulation on such worlds could transport different types of exotic materials to different regions, creating precipitation patterns that change both spatially and temporally. The discovery of super-Earths and mini-Neptunes, which are planetary types that don't exist in our solar system, has opened up new possibilities for exotic atmospheric phenomena. Some of these worlds orbit close enough to their stars to experience extreme heating, while having atmospheric compositions that are different from gas giants. These planets might experience exotic precipitation involving materials that are solid under Earth conditions, but become atmospheric components under the extreme conditions of close stellar orbits. Observations of the super-Earth 55 Cancri E have provided tantalizing hints of what exotic atmospheric phenomena might occur on smaller planets. This world, with a mass about 8 times that of Earth, orbits so close to its star that its surface temperature exceeds 2000 degrees Celsius. At these temperatures, many rock-forming minerals would exist as vapors in any atmosphere the planet might retain, potentially creating exotic precipitation patterns involving vaporized basalt, granite, or other common rocky materials. The frequency of exotic precipitation planets also depends on the evolutionary history of planetary systems. Planets that migrate inward from their formation locations may retain atmospheric compositions that reflect their origins in the cooler outer regions of their stellar systems. These migrated atmospheres might contain materials that create different types of exotic precipitation than planets that formed in their current close orbits. The age of planetary systems also influences the likelihood of observing exotic precipitation. Young planetary systems may have more debris and volatile materials available for creating exotic atmospheric phenomena, while older systems may have evolved toward more stable atmospheric configurations. The ongoing bombardment of planets by asteroids and comets also provides a continuous source of new materials that can participate in exotic atmospheric chemistry. Current observational surveys are actively searching for signs of exotic precipitation on hot Jupiters and other extreme exoplanets. The Transiting Exoplanet Survey Satellite, or TESS, has identified thousands of new hot Jupiter candidates that are being studied with ground-based and space-based telescopes to search for signs of exotic atmospheric phenomena. Many of these newly discovered worlds show preliminary evidence for high-altitude clouds and atmospheric dynamics that could indicate exotic precipitation processes. The James Webb Space Telescope is revolutionizing our ability to study the atmospheric compositions of hot Jupiters and other extreme planets. With its unprecedented infrared sensitivity and spectral resolution, JWST can detect the signatures of exotic atmospheric materials and track their behavior as they move through planetary atmospheres. Early JWST observations have already revealed new details about the atmospheric chemistry of several hot Jupiters, including evidence for previously undetected exotic materials. Ground-based observatories equipped with advanced adaptive optic systems and high-resolution spectrographs are also contributing to the search for exotic precipitation planets. These instruments can detect the Doppler signatures of rapidly moving atmospheric materials and track how exotic clouds and precipitation patterns evolve over time. The combination of space-based and ground-based observations is providing an increasingly detailed picture of atmospheric diversity among extreme exoplanets. Statistical studies of large samples of hot Jupiter planets are beginning to reveal patterns in the occurrence of exotic atmospheric phenomena. These studies suggest that exotic precipitation may be more common around certain types of host stars and in planetary systems with particular characteristics. As the sample sizes continue to grow, astronomers will be able to identify the key factors that determine which planets are most likely to experience different types of exotic weather. The search for exotic precipitation is also being extended to planets around different types of stars. Red dwarf stars, which are smaller and cooler than our Sun, but make up the majority of stars in our galaxy, host many close orbiting planets that could experience exotic atmospheric phenomena. The lower stellar temperatures around red dwarfs might create conditions favorable for different types of exotic precipitation than those observed around Sun-like stars. Brown dwarfs, which are objects intermediate in mass between stars and planets, provide another laboratory for studying exotic atmospheric phenomena. Many brown dwarfs have atmospheric temperatures and pressures similar to those found on hot Jupiter planets, and some show evidence for clouds composed of exotic materials like iron droplets and silicate particles. The study of brown dwarf atmospheres provides insights into the atmospheric processes that might occur on the most extreme exoplanets. The growing catalogue of exotic precipitation planets is revealing that such phenomena represent a major category of atmospheric behavior throughout the universe.